Hello. Um, hmm. I'm trying to get Zoom set up. Every time I use it, it seems like it's set up differently. Okay. Do you see, is everybody? Can you hear me? Do you see the desktop?
Yeah, we can hear you and see you.
Okay, great. Uh, hmm, okay. All right. I'm still trying to understand how Zoom is laying out things for me. All right. So we're going to continue today talking about processes. Okay. And there's a homework assignment, a program assignment due today. Okay. There'll be another one up soon. Did anybody have any question about this one? It's due today. And is there anybody who's got a question? Does anything odd come up or anything? Anybody have notice anything or want to ask about something?
No, I think we're good.
Yeah, there'll be another program assignment up in a couple of days. So if you have questions about this one, send me email. I have office hours tomorrow. It's important to get it done. So if you don't get it done tonight, you can still ask questions about tomorrow in office hours. Okay. So the important thing is to try to make sure to try to do as much of it as you can. Okay. So what we're going to talk about are processes, and what we're going to be doing is trying to approach processes by drawing pictures. Okay, because operating systems if you just read the theory, it can be kind of hard to figure out. And I think if you draw a picture of what you think a computer is doing, it can help a lot in building up the idea of what an operating system is doing. So let me I drew some pictures to try and build up the idea. We were doing this a little bit the other day. Okay, right, like this was our picture of a CPU. I mean, this is everyone's picture of a CPU. And what you have to remember is that the CPU, the program counter is an address in memory. So actually, yeah, well, the program counter holds every memory location has an address. They go from most people's computers right now, they go from 0 to 2 to the 34 because most people have around anywhere from 4 to 8 gigabytes of memory. 2 to the 34 is 8 gigabytes of memory because 2 to the 32 is 4 gigabytes of memory. So that's how many memory locations you have. The program counter holds one of these numbers in binary. Okay, that points the program counter at a memory location. The program counter fetches what's in that memory location into the instruction register. It decodes what's in the instruction register, figures out, is it a load instruction, a store instruction, an add or a multiply instruction. Then it does the instruction, it executes the instruction. If it has to load one of the registers, it will go get data into one of the registers. If it's supposed to add two registers together, it can do that. So you have what's called the CPU instruction set. The instruction set, yeah, the instruction set is the set of all instructions the CPU can do. So you can just Google instruction set and you get pictures like a simplified instruction set. That binary, like this would be, a lot of times people just do this to make up an imaginary instruction set. The idea is the binary number 0 is subtraction. The binary number 1 is add. The binary number 2 is another kind of add. Binary number 3 is an OR. So that's how computers work. Every possible binary pattern you can find in memory, when it's loaded into the instruction register, is some instruction that the CPU can do. The Pentium computer has thousands upon thousands of different instructions it can do. If you look up the Intel instruction set, there's a bunch of websites that give it. It's monstrously big. This is not the whole instruction set. This is a summary of it. This is a summary of all the instructions, and they don't give you, for example, the binary value for every instruction. There's a website out there. I wonder if I can find it real quick. That gives a really good binary summary of the entire instruction set. I probably doubt if I can find it by just accident. Oh, see pictures like this. See, people think this picture here is just a version of the one we're drawing, a slightly fancier version of the one we're drawing. Memory, CPU. The Intel CPU has a whole slew of registers. It's got about 15 different kinds of registers. And then each kind of register has a whole bunch of registers. Okay, so this would be a picture of a CPU. Now he kind of, this is the CPU and this is memory. Okay. Oh, and he notice how he draw memory 0 at the bottom, 2 to the 64 up at top. Some people draw memory with 0 at the top, highest number at the bottom. Some people draw it with lowest number at the bottom, highest number at the top. It's just, there's no right way to do it. Okay, but the address space in a modern computer, the actual address space goes to 2 to the 64. That doesn't mean you have that much memory. I drew here is the memory. He's drawing here the address space, and we'll eventually get to the difference between these. The memory and the address space are not the same thing. They're very closely related, but they're not quite the same thing. So he's imagining this picture of the address space, and I'm saying I'm imagining the actual memory that's in your computer. Okay. Right. So this kind of way of thinking is pretty common. I wish I could find that one website. There's a really interesting website. I think it's this one. You can look up every instruction by its binary value. And this is really, some people need this level of detail, but this is the binary, every possible binary value and what machine instruction it represents. It's kind of an interesting site. If you, every once in a while, depending on what kind of level of programming you're doing, this stuff can be very useful. Okay, but it's in numerical order, starting at 0. Every possible binary value that you can find in memory, and what machine instruction, what CPU instruction it is. Okay, and this is probably not even the complete table, because the complete table would have probably hundreds of thousands of items in it, because there's so many variations on these instructions. Okay, so that's our idea. That's our beginning idea, is that the program counter holds the address, which is essentially a pointer. The program counter is a pointer. It holds the address of a memory location. When you turn on the CPU, whatever number's in there, the CPU goes to that address, grabs what's in it into the instruction register, figures out what to do with it. And it just does this forever. The CPU never does, like modern CPUs don't have a notion of halting. You can't stop the CPU. You have to turn the power off to it. In the old days, you could stop a CPU, but the modern Intel CPU doesn't ever stop. It just keeps running. It never stops doing this. And if it's got no work to do, what's interesting is that when it has no work to do, if you go over here and bring up Task Manager, and you go to the details list, see if I can remember which one. See this system idle process? That's where the CPU parks itself. There's one process that is just a little infinite loop, do nothing, and that's where it puts itself when it does nothing else to do. When the CPU has nothing to do, it doesn't stop, it just idles, and essentially it idles by, it's just a little like for loop that just says while true. It'd just be a little for loop that says while true, waiting for something to happen that it needs to take care of. You notice that my CPU is spending almost 90% of its time doing nothing. But when it has nothing to do, it does not stop. It puts itself in the idle process, which is just an infinite loop. CPU never stops. So it's doing fetch, decode, execute. As long as it has power, it's doing fetch, decode, execute. Okay. So now this is a picture of a CPU running essentially one process, because the CPU is just doing one, what we refer to as instruction stream. Okay, it's an important idea, but it's stepping through a stream of instructions because every time it executes an instruction, the program counter, as part of the execute, the program counter gets updated to another instruction. More often than not, the next instruction to do is the one right after the one you just did. So if the program counter is holding 10, so you're at memory location 10, then after you did that instruction, the program counter would point at 11. Then you do what's in instruction 11. Then after it did what's in instruction 11, you point to instruction 12. But some instructions jump, like function calls and if statements. So some instructions jump you somewhere in memory. So as part of the execute, you update the program counter. More often than not, it's just incremented by 1, but sometimes it'll be set to a specific memory location to jump to a function or to branch in an if statement. The sequencing of instructions in memory is called an instruction stream. The CPU can only do one instruction stream. And our goal is to figure out how the heck does it run? How the heck does it run all these programs simultaneously? Like, notice I'm running multiple programs simultaneously, but the CPU can only run. The CPU only does one instruction stream at a time. Okay, and we want to learn the details of how a modern operating system creates the impression, which is actually, I mean, the key idea is it creates the impression that it's running more than one program because it's only running one program at a time. It's only doing one instruction stream at a time. And we have to build up precisely the idea of how it can pretend to do and one way you could pretend to do multiple instruction streams at a time is that in fact that this computer has 12 CPUs. So potentially each CPU could be executing a different instruction stream, but that still doesn't solve our problem because I have way more than 12 processes running here. And I could easily come up with more than 12 programs running on my desktop. Like right now, I've got a half a dozen at least running right now. There's this program that's drawing a picture, and then there's the Explorer that's drawing these windows, and then there's Zoom running in the background, and there's a timer running in the background, and there's Chrome running in the background, and Chrome is running multiple tabs, which we know are each tab is its own process. So easily I have way more than 12 processes. So it's not that the computer just can run more than one program because it has more than one CPU. That's part of it, but that's not the interesting part. The interesting part is how can one CPU pretend to run more than one program? That's our real goal. So I'm going to keep drawing just one CPU. How does one CPU pretend to run more than one program? Okay, so now here's a picture. Here's how we're going to imagine it. We're going to imagine that there's a disk drive, and on the disk drive there are EXE files. Okay, we know that EXE files are what you create processes out of. So when you want to create a process, so I'm imagining that here's memory. I'm imagining it's really large, and one part of memory is dedicated to that program. So that program's been loaded into memory. That means all the data in that program is just copied into memory. And this program file was copied into memory. So I've got two processes, but I've only got one program counter. Yeah. So I want to start talking about how this CPU can pretend to run these two programs. Okay. The bottom line is it switches between them. It runs this one for a little while, then it runs this one for a little while, then it runs this one for a little while, then it runs this one for a little while. That's the heart of the matter, and that's called time slicing. Okay? And if you go over here, if you just Google time slicing, it's what an operating system does. Okay, it's an operating system idea. Time slicing is the idea that you're going to slice up time as some time is given to this process and then some time is given to that process. So you're slicing up time, but the question is, how does this work? How do you get the CPU to jump from one to the other? Okay, and that's what we're going to talk about. How do you get the CPU to go from this instruction stream to this instruction stream, and how does it go back to this one? Okay, there's more than one way to do the time slicing. The idea is time slicing, and then there's multiple ways of creating time slicing. Okay, we're gonna think about two ways of doing time slicing: an old-fashioned way and then the modern way. The old-fashioned way is not even mentioned. I don't think it's mentioned in our textbook. And then the modern way is what the chapter in the book is really about. Okay, so the key to this is you got to put a third process in memory. Okay, you have to put a third process. I'll draw it in. What you have to do is you have to imagine that there's a third process in memory. And the third process, so I'm going to draw it as here's a third process sitting in memory. Okay. And that third process is going to be what we call the operating system. Okay. So the operating system is essentially a process sitting in memory. So this is the operating system. Oops. Okay. So there's a process in memory called the operating system, the OS process. Okay. Right. And in the OS process, there's a function called yield. This is the old-fashioned way of doing it. Okay. There's a function called yield. Suppose that the operating system is running this process here. So I'm sorry, suppose the CPU is running this process here. Okay. At some point, this process can call the operating system's yield function. So suppose here it calls yield. What yield means is it's its way of saying to the operating system, I'm giving up the CPU. You can do whatever you want with the CPU. I'm done with it for a while. When this process calls yield, actually over here, so this is the yield definition. So over here is the yield code. Okay. So the process calls yield in the operating system. And what that's doing is giving up the CPU. This is one mechanism for how a process can give up the CPU. Okay. So the process just says, I don't really have any more work to do. So it calls yield to give up the CPU, to process the CPU to the operating system. If the operating system knows that this process has work to do, well, this process at some point it had also called yield. So what you have to imagine is that somewhere down here, it had also called yield. The operating system returns to its yield function. Then this guy runs, and then when he's decided he's had enough work to do, he yields, which calls the operating system. And the operating system returns to this yield. Okay, and then that makes this thing run for a while. Then when this thing returns from yield, it does some work. Then when it's decided it's done enough work, it calls yield, which goes to the operating system. And the operating system has some bookkeeping in it, so it keeps track of how many yields it's got going. Like maybe I'm just showing there's two of them. There's two processes. So the operating system does some bookkeeping so that when one of the processes yields and calls this function can schedule or decide which one of the yields to return to. It could return to this yield, for example, and let this guy run for a while. And if there's no other processes running, this guy can just do the idle process for a while, then return to this to see if this thing has any more work to do. If this thing has no work to do, it'll just yield right back to here. Okay, this is called cooperative multitasking. Okay, this idea existed for a long time. It's called Cooperative Multitasking Operating System. So it's got its own Wikipedia page. It's a way of designing operating systems. Okay. See, this one says preemptive multitasking. That's what we're learning. We need to learn about. Preemptive multitasking is it's what the textbook's all about. That's what we're really going to be doing. Okay. But this idea of cooperative multitasking is how Windows used to work when it was first created. It's how DOS used to work when it was created. It's actually even how Unix worked when it was first created. When operating systems were first created, back in the 70s. They did a lot of them, Windows, Mac, even at one point Linux, not Linux, but Unix. They worked in this cooperative multitasking way, using this idea of a yield. In fact, they had different names for it. Yield was a pretty common name. Okay, now what's the disadvantage of this? These processes are not independent of each other. If this process never calls yield, this process never gets to run. Okay, if this process goes into an infinite loop by accident, this process can never run, because if this thing's in an infinite loop away from the yield, it never gets to the yield. This way of designing things is not modern. It leaves each process up to the mercy of every other process. It doesn't do a good job of virtualizing the CPU. Our goal is that each process thinks it owns its own CPU. Okay, this is what we're going to get at, the idea of a virtualized CPU. This is a real CPU, but in a sense, what you want is each process to kind of think it's got its own little, you might draw a little thing here. Each process thinks it's got its own little virtual CPU. Okay, and this other actually, I should have drawn that, draw it in red, because it's that this is for that process. Okay, so yeah, what we're really kind of getting at is that each process kind of thinks it's got its own little virtual CPU. Okay, okay. And then over here, this other process would also think it has its own little virtual CPU. So this process thinks it's just running on one CPU and doesn't have any idea that this process even exists in memory. And this process should think it has its own virtual CPU, and it's really running in that virtual CPU, and it doesn't know about this process. In fact, there's just one physical CPU, the real CPU. We're trying to create this impression. And in the operating system's textbook, where's the, oh, see how this is called virtualization. The section of the book we're in is called virtualization. I kind of wish this column here is virtualizing the CPU. This column here is virtualizing memory. So we're going to create virtual CPU and virtual memory. That virtual memory is the address space. Remember, I showed you another picture that where there was a picture that showed, and I can't remember if it was here. One picture showed an address space. The address space is the virtual memory. Okay, so we're virtualizing the CPU and virtualizing the memory. Okay, and the goal is to let each process think that's got its own CPU and that this little red box is all of memory. This process is going to think that its little red box is actually all of the memory of this virtual CPU. And this process is going to think that its little red box is, in fact, all of the memory of this virtual CPU. This box won't know that this one exists, and this one won't know that this one exists. They will know that the operating system exists. So the operating system essentially is going to be part of each of their virtual CPU and their virtual memory space. So this guy's virtual memory space is him and the operating system. And this guy's virtual memory space is him and the operating system. But our goal is that neither process know about the other, okay? And they're completely separated. So if this process goes into an infinite loop, doesn't affect this one. His virtual CPU will still keep running him. I mean, that's this CPU over here, but the fact that this one goes into an infinite loop is not supposed to affect this one at all. If this one does something and blows up, that doesn't in any way cause this one to blow up. Now with the cooperative multitasking, with the yield idea, you do not actually have a virtual CPU. There isn't the virtual CPU, because if this process goes into an infinite loop, he'll never yield, so he'll never let this guy run. So this guy will when this one dies, this one will die with it. If process 0 dies for some reason, process 1 and all the processes in memory die with it. Okay, so that's kind of that's a bare bones way of creating a virtual CPU, is to have this yield instruction. And in fact, it doesn't really create the virtualness. The yield, in yield, they're pretty much explicitly saying I'm sharing this CPU with everyone else. So each process calls yield to share the CPU. Okay, so if you for the what we really want is this picture here without the yield. We want this picture here where each process isn't yielding, where each process is just running without any knowledge of the other process. So this is actually what we want. We want this process to have its own virtual CPU and this process to have its own virtual CPU and not have any idea that the other processes even exist. So now the question becomes, how do we do this? If we're not going to do the cooperative multitasking, let's save this. Okay, I don't know what that means. Okay, what's a better way to have two processes in memory sharing one CPU? Right now, we've been talking about the yield idea, which they literally are sharing it, and they have to cooperatively share it. If one of them hogs the CPU, then that's a real problem, and that was a huge problem in the 80s and 90s with the early versions of Windows and Mac operating systems. If any one of the programs on your computer crashed, you would usually have to reboot the computer and lose all the work you had in all your other open programs. If you had 3 or 4 programs open and one of them crashed the computer, all the work and all the other open programs was lost. And that was the way we lived back then. Computers were very unreliable in that sense. And as Intel CPUs got more and more sophisticated, they got better at this. Because the solution to this problem is to add hardware to the computer. We're going to see that to do real multitasking, to create these virtual CPUs, the way it's going to be done is by adding hardware, adding architecture to the CPU. And that's why I kind of want to do this at a point of view of thinking of the architecture class, because the real solution, operating systems don't exist without architecture. Operating systems and architecture are just completely intertwined with each other. You can't modernize operating systems without changing computer architecture. And almost everything these days that's done to design computer architectures to make operating systems run better. So you should think of operating systems as just sitting right on top of the architecture course. It's just an extension of it. In fact, a lot of schools use books that combine architecture and operating systems in one book. It's not that unusual for this is to be taught like as a one-year course of combined architecture and operating systems. Okay, they're really closely intertwined because you can't build an operating system without adding new features to your CPU. Okay, all right. So now we want to go to two processes, but not cooperatively multitasking. Okay, so what are we going to do? Okay. Okay, let me want to add to that picture. Okay, so what we're going to do is add something to the CPU. Okay, what we're going to do is add a little box over here called a timer. Okay. So there's this device called the timer. It's a piece of hardware. It's on the motherboard of the computer. Okay. And the timer is connected to the CPU by what's called an interrupt. Okay. So the timer is connected to the CPU in what's called an interrupt. Okay. So this is referred to as an interrupt. Okay. Whoops. Now what that means is what happens is the timer is set to a common value these days is 50 milliseconds. Okay. Every 50 milliseconds, the timer sends an electrical signal. This is all inside the computers. This is all done with electric currents. The timer sends a signal on this wire to the CPU. Okay. It interrupts the CPU. Okay. Now, what that does is the CPU, when it sees that interrupt, the CPU halts what it's currently doing. So suppose the CPU was at that point, suppose the CPU was in that process. So the program counter held that memory address. So the CPU is doing this instruction stream in here. Okay. When this interrupt happens, the hardware of the CPU replaces the program counter with a fixed value, okay, that redirects the CPU somewhere into the operating system. That's called an interrupt vector. Okay. So when the interrupt signal happens, the operating system or the CPU hardware forces a specific value into the program counter, and that specific value puts the program counter inside where the operating system sits. That's kind of like this replaces the yield. Okay, so instead of having a yield function, in fact, you could, even if you wanted to, you could call it yield. You could think of it as a yield function inside the CPU, inside the operating system. But programs don't call yield. They're forced to call yield by this interrupt vector signaling, this interrupt connection signaling the CPU. The CPU, instead of one process calling yield, the CPU forces into the program counter the address of this yield instruction, and then the operating system starts doing its work. And at this point, the operating system does something similar to what it did before. It says, I'm going to switch from one process to another process. I'm going to do what's called a context switch. I'm going to switch from running one process to running another process. Okay, so what the operating system will do is when it gets forced into the yield, the operating system, we'll talk about the details of this, but the operating system looks into some bookkeeping and it says, well, process 0 is running, and I know that there's a process 1 that should run too, so I'm going to give the CPU to process 1. So the yield thing, it's actually a better name for it would be scheduler. You know, the term we're really going to use for it is you're inside what's called the scheduler of the operating system. So this, instead of being yield, should be schedule. The scheduler will say, I'm going to give the CPU to this other process. Okay. So then the CPU puts the operating system puts a value in the program counter that directs the program counter into this process. And this is real important. The operating system will cause a program value to be put into the program counter that directs the CPU into there. And then the CPU is running this. And it stays there until 50 milliseconds later, this interrupt happens again. When the interrupt happens again, the hardware, it's important, the hardware in the CPU forces into the program counter the address of the scheduler / yield, whichever one you call it. The scheduler in the operating system says, okay, this guy's had his turn. Now it decides what process gets its turn next, and it redirects the program counter into the other process's memory space. And what it's really supposed to do is it's supposed to pick up where the other process was when it got interrupted. Notice that when this thing fires, when this interrupt fires, this process was somewhere. So he got interrupted at that point. And then the program counter got directed into the operating system. The operating system needs to keep track. Part of its bookkeeping has got to keep track of exactly where this thing was when it got interrupted, so that when it decides to return to that process, it can put into the program counter the very next instruction that this thing was about to do. And we're going to see how that bookkeeping gets done. That's what the textbook is about, these kinds of things. These bookkeeping ideas and making precise all these ideas. Right now, we're kind of sketching the rough idea. The rough idea is not that complicated, and then we'll fill in the details. The rough idea is the key idea is this interrupt over here, the thing called an interrupt. And interrupts are something you should have seen in the architecture class, because interrupts are fundamental to how hardware works. Interrupts are also, I didn't draw it in here, like how does the CPU talk to the disk drive? Well, it turns out that the CPU talks to the disk drive by an interrupt. The disk drive and the CPU also connect to each other by an interrupt. Okay. And that's actually how hardware and the CPU talk to each other. The disk drive has its own interrupt into the CPU so that the disk drive can essentially send messages to the CPU so they can communicate. Okay. So interrupts are fundamental to how modern computers work. Hardware talks to the CPU or interfaces to the CPU through these interrupts. As part of creating multitasking, we need this one real important interrupt called the timer interrupt. It's one of many interrupts on a modern CPU, but it's the one that's most crucial to us right now. The timer, and not all operating systems use the same amount here. 50 milliseconds is real common. In the tens of milliseconds is the common values. Some books will tell you, oh, it's set to time every 20 milliseconds. Now notice that's real fast. Every 50 milliseconds, that means you jump from this process to this problem every 50 milliseconds. And like I have, like on my machine, I have all these processes. If each one of them is given 50 milliseconds, think in any 50 milliseconds, how many 50 millisecond units are there in 1 second? Okay, 50,000. Yeah, I can. It's quite. In other words, in all of these processes will be given a chance at least every about half second or more, probably much more than that. Okay, if you're giving each process 50 milliseconds to run, then the next one gets 50 milliseconds to run, and the next one gets 50 milliseconds to run. While the CPU is running this one, like this program is actually most of the time not running. You have to realize right now, most of the time, this program is not running, but it gets its 50 milliseconds every couple hundred milliseconds. So every like 3/10 of a second, this thing gets its 50 milliseconds. That's good enough for it to create this impression here. See? And it work. Yeah. And if I were to try to run thousands of processes on my computer, if I were to try to run thousands, I would start noticing a problem. Because if I tried to run thousands of processes and I gave each one of them 50 milliseconds, after one process got its 50 milliseconds, it might be several seconds before that process got the CPU back again. I would then start seeing the limitations of this. But nobody runs thousands of processes on their CPUs, okay? Nobody runs thousands of them. Okay, they do sometimes run hundreds of them, but not in an interactive environment, like on servers and in large data centers. It might be a case that one CPU is running hundreds of processes, but probably never thousands of them, because the operating system virtualization starts to break down. A process could go seconds between its turn to do work. If this is we call this the time slice. If the time slice is 50 milliseconds, but there's thousands of processes, you're going to go, well, you could go a whole minute without seeing the CPU. One process could go a whole minute without ever seeing the CPU. Okay, so this works if there's dozens to hundreds of processes. Then the processes will see the CPU several times a second, and they can pretty much fool people into thinking that they're running all the time. Okay. All right. So this is the key idea here. that we add to the CPU this interrupt hardware. Okay, that wasn't in the original model. Oh, if you buy a really super cheap CPU, the kind of CPU that might just do one thing, like what there's CPUs out there you can buy for pennies, that the kind of thing you would put inside of a little a cheap wristwatch or a cheap toy. And they don't have even things like interrupts. Their program counters run only one process and just keep running it all the time. If a CPU is running the logic inside of some simple toy, it only has to do one thing continuously. Okay, so the idea of a CPU doesn't include the idea of an interrupt. The idea of an interrupt is something you add to the CPU to make it more sophisticated. The key idea of a CPU is a program counter and registers and memory, and that the program counter does the fetch, decode, execute cycle on instructions in memory. A program counter, instruction register, registers, and memory are the heart of a CPU. You can't have less than that and call it a CPU. But then you can add to it, like an interrupt. And an interrupt is an important thing to add. The interrupt, first of all, gives you external hardware. So the interrupt is also usually how the CPU would deal with external devices. In our case, with the timer interrupt, it's how we can start supporting the idea of multiple processes that don't know about each other, processes that don't know that the other processes exist. Okay. Now, that means inside this CPU, there's got to be logic so that when this signal happens, the logic inside the CPU notices that signal, forces an address into the program counter, and then that address, and that address that it forces into the program counter is determined by Intel. Actually, that's part of the CPU architecture. So the people who write the operating system need to know what that address is because that's where they put the operating system. The operating system sits in memory at the place where these interrupts force the program counter to go to. So the area in physical memory where you put the operating system is kind of determined by the architecture of the CPU. Because when this interrupt happens, this interrupt puts a different address into the program counter. If you have every one of your hardware devices has its own interrupt. So you have lots of hardware devices here. You have a GPU, or you have a NIC, a network interface card. Okay, the NIC is the thing that talks to the network. The NIC has its own interrupt. Okay, so it's got a different interrupt into the CPU. When the NIC wants the CPU's attention, the NIC interrupts on a different interrupt than the others do. That directs the CPU to code that handles the NIC, and that's what we mean by device drivers. Device drivers are the code that these hardware devices interrupt into. So the disk drive, when it launches that interrupt, it's sending the program counter into its device driver. When the NIC raises that interrupt, it's sending the program counter into its device driver. And when this thing raises its interrupt, it's actually kind of setting. I mean, this thing we call the yield, you can think of it as the device driver for the timer. It's kind of what it is. It's kind of like the timer's device driver. When the timer signals its interrupt, it wants this program counter to go into the code in the operating system that is what handles the switching, the scheduling code, the switching between processes. Okay? Every interrupt sends you to a different chunk of the operating system that handles what that interrupt does. Like, this interrupt would send you to the chunk of the device driver for the hard drive, which would communicate with the part of the operating system that does the file system. This would signal the device driver that talks to the part of the operating system that does networking. Okay, and this interrupt takes you to the part of the operating system that does what we call scheduling. It decides what process should be run next. And in the course, you see how we're going to get to a chapter on CPU scheduling. Okay, and the second half of this chapter is all about scheduling. In fact, all of these sections here are actually scheduling sections. These things, chapters 7, 8, 9, 10 are all about scheduling. That's the theory. That's actually where most of the theory is. The theory is about mostly how do you decide who gets to run next. When the timer interrupts the CPU and says, it's time to leave the current process and go back to the operating system. Most of the work in operating system theory is what's a good strategy for deciding who should run next. There's all these issues of priority and something called starvation. So there's a lot of work in deciding who is the next process to give the CPU to. Okay, so in the textbook, what we're talking about right now is chapters 4 and 6, processes and what we're this direct execution. This is the idea of this interrupt and timer and all that. Okay, so we're actually kind of what we're talking about is a blend of chapters 4 and 6. Now notice he doesn't draw any pictures. Yeah, he manages to talk about all this without ever drawing a picture. He's supposing that in your architecture course you saw lots of pictures. I'm sure he wrote this with a picture in his mind. I mean, everybody pretty much has a picture in their mind when they think about these things. He probably had one in his mind, and he probably assumes that you have one in your mind too. But I don't think especially when people are starting out, I don't think you guys have a good picture in your mind. I think it's important that you start building a picture in your mind. So, I think it's real important to draw these pictures. And some books do draw more pictures and some books don't. So I think it's important to draw pictures because the visualizing these ideas as a picture can help you really remember what's going on. Okay, but there's parts of it that I don't put in the picture, like this idea that there's hardware in the CPU. You have to know what this interrupt does. The picture kind of helps you think there's an interrupt, but the picture doesn't tell you what an interrupt does. The important thing you have to remember is when 50 milliseconds expires and this thing is what we call signaled, that forces, using the hardware, some logic in the CPU, forces a specific address in the CPU, which directs the CPU to a new instruction stream inside the operating system. Okay, so that takes you away from this instruction stream, forces you into that instruction stream. Okay, so then the CPU is in the scheduler and decides who to go to next. Okay, now there's a lot of things we're not mentioning here that we have to talk. Like, this is supposed to create the issue of a virtual CPU, but it's still not enough of a virtual CPU. For example, inside the CPU, there's an instruction for turning off interrupts. You can turn these interrupts all off. That's necessary for various technical reasons. So what if process 0 wants to hog the CPU? Process 0, if it's a clever programmer, he'll know what CPU instruction disables interrupts, and he'll disable the interrupts. So once process 0 disables the interrupts, that's like you go back to the yield, the cooperative multitasking. If you never call yield, you can hog the CPU. If this process, it disables interrupts, while the interrupts are disabled, he can run for all he wants. Now, that may be kind of drastic because disabling interrupts turns off all the I/O devices. But in fact, you can disable interrupts individually, like you can just disable the timer interrupt. Or he could do a different thing. If he knew what he was doing, if he knew how to program the timer, he could change that timer from 50 milliseconds to, say, 5,000 milliseconds or 100,000 milliseconds, and essentially get huge chunks of CPU time by changing what's the amount of time in the timer. So what's going to stop a malicious process from essentially breaking the rules and going in here? And see, the idea is that we haven't really created a virtual CPU. This guy is running on the physical CPU. The physical CPU can turn off interrupts. So why can't this guy just turn off interrupts and just keep running on the physical CPU all he wants? We haven't quite yet really built a virtual CPU yet. He's not running on a virtual CPU. He's running on the full-fledged CPU, and he knows it, so he can disable interrupts or disable the timer interrupt or change the value in the timer interrupt so he gets a really long amount of time to run. Okay? All right. So there's got to be more hardware in the CPU. Okay? There's got to be more hardware in the CPU that somehow solves this problem of actually creating the virtual CPU. Okay, so here's what we're gonna do. We add another little piece to this puzzle. Okay, I'm gonna put a little box in here. inside the CPU, there's going to be a little box. That box is called the mode bit. It's just a bit. Okay, so that bit is either 0 or 1. So this inside here is a 0 or, I'm sorry, is a binary 0 or a binary 1. Okay. Right. So we have the mode bit, which is either set to 0 or to set to 1. Okay. Here's how that works. The mode bit determines whether the CPU is in one of two modes. The two modes of the CPU are kernel mode. And if we want, we can just arbitrarily pick 0. We'll say 0 is kernel mode. And the other mode is called user mode. Okay. So if this bit is set to 0, the CPU is in kernel mode. If this bit's set to 1, the CPU is in user mode. The user mode is essentially this virtual CPU. This is the brilliant idea that some engineer had long time ago. Okay, that we would put a bit in the CPU. When the bit is 0, now when the CPU is in kernel mode, the CPU is got all its features, has access to all its features. So that means that the CPU can do everything, turn off interrupts, do anything it wants. When the CPU is in user mode, the CPU is essentially a virtual CPU. It's restricted. The CPU is now in a mode where, for example, it cannot turn off interrupts. Okay, so that's how this guy is prevented from doing something like turning off the interrupts. When this here's how it works. The program counter is running here inside of a process. It's in user mode. Okay, so the CPU is a virtual CPU. It's really this CPU, but it's this so the virtual CPU, if I want to think about it, the virtual CPU is, you can think of the virtual CPU as it's the CPU with that bit set to 1. See, I can't draw this very well. I think I almost got it in there. Yeah, there. Okay. Okay, that's what a virtual CPU is. The virtual CPU is the CPU in user mode. Okay, that's what our virtual CPU is. It's the CPU in user mode. The textbook has a funny name for this. The textbook calls it limited direct execution. Limited direct execution is their fancy name for user mode. The CPU is being put in user mode. Okay. So, and he calls it user mode too somewhere in here. I forget. He thinks of it as, it's in a limited, the CPU is limited. I think he calls it user mode at someplace. Okay. Most people in the world of operating systems refer to this as kernel mode and user mode. Okay. All right. So the CPU is in user mode running this instruction stream. Okay. This timer interrupt fires. The hardware now does two things. The CPU hardware forces an address into the program counter that redirects the CPU into the operating system, and it switches from user mode to kernel mode. Okay. When you're in user mode, there is no way to switch to kernel mode. The only way to switch to kernel mode when you're in user mode is for there to be an interrupt happening. The interrupt, which your program doesn't control. Your program doesn't control these interrupts. So when one of these interrupts and it doesn't matter if it's any one of the interrupts does this, because all these interrupts force an address into the program counter, which directs you into the operating system. When you're in the operating system, you should be in kernel mode, because that's what we call the operating system. We call it the kernel. This is the part of the operating that we're really talking about. Actually over here, I should have said the OS kernel, because there's parts of the OS that aren't the kernel, but this is really the operating system kernel that we're really talking about here, the very heart of the operating system. So, for example, the task manager is part of Windows, but it's not part of the kernel. Explorer, the part that draws all these windows, this is part of Windows operating system. It's not part of the kernel. The Explorer is just another user process like these are. The Explorer, and this is actually kind of important, the Explorer is not running in kernel mode. It's not part of the operating system kernel. Okay. If you call up the task manager and you wonder which of these guys are part of the kernel, it's a little bit hard to tell. See, some of them have username system. Some of that's the kernel, but some of these have no username. They're not identified as being, some of this is part of the kernel and some of it isn't. Some of it actually is the kernel. And I forgot, I used to know which parts were part of the kernel over here. I've forgotten over the years. It's not very important from our point of view to know which one of these is part of the kernel. That one might be, I can't remember. I think it might be. This is the window manager. I don't think it's part of the kernel. See, this DWM stands for desktop window manager. That's the thing that the Explorer runs on top of it. That's that guy. Now he's not something we can kill like we can kill the Explorer. The Explorer is actually running on top of the desktop window manager. I don't remember if he's part of the kernel or not. I have a feeling he isn't. But he's lower level than Explorer. See, Explorer is running as me. I can kill the Explorer. It's just running. The Explorer is just another process. It's just another process like any other user program. The Explorer is no more privileged than Notepad. Okay, but Explorer runs on top of the desktop window manager. See, it doesn't say here what user it's running under. It might be, I can't remember if it's part of the kernel or not. Okay, all right. And then if you go through a lot of these, anything that says this is not the kernel. That's me. That's a process that's running as essentially I'm running it. Okay. The ones that have no name here, some of them are part of the kernel and some of them aren't. Okay. Like that one, I think that one, oh, here, system interrupts. Yeah. That's got something to do with handling all these interrupts that come in. There's even a process called system interrupt. Okay. Notice it doesn't even have a process ID number. Okay. The system idle process is process ID 0. See, this one's ID 4. So that means it was only the 4th process created after booting. Okay. So these are very low level processes, but they may or may not be part of the kernel. I do not remember exactly who is and who isn't part of the kernel in Windows here. Okay. All right. So the kernel, by definition, is what runs in kernel mode. Device drivers are part of the kernel. Device drivers don't show up in that list of processes. And device drivers aren't quite technically processes. They run in a slightly different way. Device drivers run in kernel mode. And that's actually considered a controversial thing. There's many people think that Windows should be redesigned so that device drivers do not run in kernel mode, because crashing device drivers are one of the more common causes of what we call blue screens. When a computer really does crash, when Windows actually literally crashes and you're forced to reboot it, 9 times out of 10, that's caused by a device driver. 9 times out of 10, it's a device driver that caused something to go wrong. And since the device drivers are in kernel mode, when a device driver screws up, the whole operating system is screwed up. And there's people who think that the operating system should be redesigned so that device drivers are not part of the kernel. Okay, but right now on Windows they are, and I think on Linux they are also. The device drivers are part of the kernel. By definition, the kernel is whatever runs when the CPU is in kernel mode. When an interrupt comes in, the program counter is forced into a certain address, and the kernel mode is turned on. When the operating system is about to jump to back to your process, the last thing it does is put your address in the program counter and switch you to user mode. The CPU, there's a special instruction that the CPU has that the operating system use to jump back to user code in user mode. Okay, so when your program starts executing, your program is stuck in user mode. Okay, now here's another question. If this guy's stuck in user mode, he can't turn off timers. Okay, but what if he just goes in and erases all this operating system code? What if he just copies his own code up into this memory location? Programs can copy data all over the place. So what's to stop this program now from copying code up into here to essentially say, like a virus saying, no, don't run Windows, Microsoft's operating system code, run my operating system code, so that every time this timer interrupt happens and you switch to kernel mode, you're running my code anyway. Okay, so what's going to keep this virtual CPU from accessing this memory? For that matter, what keeps them from accessing this guy's memory? And that's more hardware, but then that brings up the virtualized memory part of the book. Okay, so right now we're talking about virtualizing the CPU, but virtualizing the CPU is intertwined with virtualizing memory. And right now we're only talking about virtualizing the CPU. We have to leave a hole in our discussion. Right now there's a hole in our logic. Why? We've just said that there's user mode, kernel mode. That's the thing that keeps this guy from taking over the timer. But what's to stop this guy from taking over the code in the operating system? He can just write his own code into those memory locations so that when this timer interrupt fires, his code has been copied in there and it's executing. Something has to protect memory. So when you're in user mode, there has to be something that says you're only allowed to talk to this part of the memory space. That's what we call the virtual memory. So this red box is the virtual memory space, and this red box is the virtual CPU, the CPU in user mode. When you set this up right with the hardware, and what we're going to do is we're going to put another box in the middle here called the memory management unit. Now, this is something we're going to talk about chapters from now, but what's going to happen is the CPU does not talk to memory. The picture is going to look like this. The CPU talks to the memory management unit, and the memory management unit talks to memory for the CPU. And this guy essentially is he's kind of part of the CPU. We'll think of him as a separate thing, but in fact, he's part of the CPU, kind of like the mode bits part of the CPU. This memory management unit will sit between the CPU and memory, and it's going to protect memory. So when you're running this process, if the CPU tried to access this memory location, the memory management unit says, no, you can't go down there. The memory management unit will say, no, you can't go up there. The memory management unit will say, well, this virtual CPU running this virtual process, all its memory addresses must stay within this bound. Okay, so we're gonna have to learn how that works. That's more hardware in the CPU. It's the part of the CPU called the memory management unit. It used to be a separate thing. Back at one time when you bought an Intel CPU, if you didn't have much money, you got a CPU without a memory management unit. Then if you had more money, you bought a CPU with a memory management unit, and your computer crashed less. You could run a fancier version of Windows, but you actually had to buy the memory management unit as a separate entity. Same with floating point. At one time, CPUs couldn't do floating point arithmetic. You had to pay extra to get these were separate chips. The CPU was one chip, the floating point unit was another chip, the memory management unit was another chip. Now, the CPU is actually all these things integrated, but we still logically think of them as separate units. The floating point unit is separate from the heart of the CPU, and the memory management unit is kind of separate from the heart of the CPU. So we'll think of it as a separate thing that sits between the CPU and physical memory, and it intercepts addresses coming out of the CPU, and it processes them, and it decides whether they're legitimate addresses or not. And if they're an illegitimate address, it halts the program. If a program tries to use an illegitimate address, something that's out of its memory space, then the memory management unit will crash the program. Okay, it'll do something to crash the program. Okay, all right. So right now, if from the point of view of the textbook, in this chapter on virtualizing the CPU, there's a hole in the logic. You can't virtualize the CPU without virtualizing memory at the same time, but it's awfully hard to talk about these two at the same time. So we virtualize the CPU and just ignore the memory for a little while. Then we kind of go in and say, okay, now let's virtualize the memory. And that kind of completes the picture. Okay, but so we at this point, when we're talking about this chapter on limited direct execution, there's a hole in the logic. Yeah, it's the hole in the logic is at that point, you have no idea how to stop this guy from modifying the code in the operating system, or how you stop this guy from modifying the code in some other process. And their answer is we don't have a way of doing it yet. It's going to be the memory management unit that protects the memory. So the memory management unit, the mode bit essentially is the virtual CPU. The mode bit, when it's 1, the CPU is, oh, here's something, suppose the mode bit is 1. Suppose this guy tries to be clever and he puts a disable interrupt instruction in his memory space. So he tries to execute the disable interrupt instruction. When the program counter fetches that instruction and loads it in the instruction register and then decodes it, it sees that it's the halt interrupts instruction. The CPU checks the mode bit. If the mode bit is 0, it goes ahead and turns off interrupts. If the mode bit is 1, the CPU halts the program. It just, what it does is it returns control back to the operating system with a message saying this process should be halted. It should just be, kicked out of memory. The process violated something. Okay, so the process is terminated. Okay, so again, if somebody puts an illegal instruction in their instruction stream, like they think I'm going to be real clever, I'm going to halt the interrupts. When the program counter will go to that instruction, fetch that instruction to the instruction register. The CPU will decode it and see it's a halt interrupt instruction. The CPU will check its logic, its internal logic, say, what mode am I in? If I'm in the user mode, I don't do halt interrupts. So what I do instead is jump into the kernel in a certain place with a message to the kernel saying the current process should be terminated. Okay, so you don't get to do funny things. Same thing with, and the memory management unit will do something similar. If this process tries to access somebody else's memory, if this process here tries to use an address, like it tries to jump the program counter into the operating system, the memory management unit will check the address that comes in. It'll say, is it in this range? And if it's not in this range, it'll send a message back to the CPU. The memory management unit will send a message back to the CPU saying, halt this jump into the kernel with this and halt this process because it violated memory. Okay, notice that this is all needs to be hardware in the CPU. The CPU hardware needs to know about the memory management unit. The CPU hardware has to know about the mode bit. The CPU logic has to check the mode bit when it executes an instruction. You can't talk about operating systems without talking about CPU architecture. This is why I think it's so important to do these pictures. You can't do one without doing the other. Okay. Okay. Oh, I lost my timer. My timer halt. I must have accidentally killed my timer. So what do we have left? About a minute? Am I right? We got about a minute. Yeah. I usually have a timer running on my other monitor, and I must have somehow killed it at some point. Okay, but yeah, luckily I noticed that we have about a minute left. Okay, all right. Now we're going to keep filling in the details of this. For example, how does the operating system do the bookkeeping? Like, suppose the CPU is right there when that timer interrupt fires. Okay, so that timer interrupt forces the CPU over here, away from where it was. Well, how does the operating system know where this process was so that later on it can go back and pick up where this process left off? There's got to be a mechanism for the operating system up here to know where this process was when it was interrupted, so this process can be restarted where it was interrupted. Similarly, when this operating system wants to give this guy a turn, the operating system has to know where to send this guy to. When the operating system wants to run this process, what program counter should be that, what value should be put in the program counter to put you back in this process? Okay, so that's going to bring up some data structures. Data structures called process control blocks. Okay, so we're going to add to this picture some data structures that live inside the operating system. They're going to be operating system data structures called process control blocks. And that's what we'll pick up. That's one of the ideas we'll pick up with. And oh, not that chapter. Okay. There's actually like a, oh, I don't remember where it is now. There's a sketch of, oh, here it is. He calls it the proc structure. Most books, and I will call it the process control block. Windows calls it the PCB, the process control block. Here's some C code that sketches, this is not the complete data structure, but it's a data structure that exists inside of the operating system where the operating system does its bookkeeping. It's going to have one of these data structures for every process that it runs. So inside the operating system will be a list of process control block data structures, one process control block for every process. And we'll see how the operating system uses the information in this data structure to keep track of its bookkeeping, to keep track of its scheduling. This data structure, you don't have access to it. It's part of the operating system. It's part of the kernel. But you can, you can learn what's in it, and we can talk about what's in it. We just don't see it. Our programs don't see it while they're running. Okay, and so we'll add to this picture this idea of process control blocks, and the process control blocks then becomes part of the data. It's not part of the hardware. The process control blocks are part of the operating system. They're a data structure belonging to the operating system. Well, actually, the process control blocks they're data structures, but we'll see that the CPU does have special instructions. The process control blocks do need hardware support to be maintained. So even though these are data structures maintained by the operating system, the operating system needs special CPU support to maintain those data structures. And we'll talk about that. And the book talks about that too. So there are, even this process control block data structure can't be separated entirely from the hardware. You need hardware support to maintain these things. Okay, so we'll start talking about that part of the picture. And then after we introduce the process control blocks, then we'll have a pretty good sense of how a modern computer manages to create virtual CPUs out of a physical CPU. The virtual CPU will be the CPU with this mode bit and a process control block. The virtual CPU will be part of this virtual CPU is part of it's the mode bit, and we'll see that part of the virtual CPU is the process control block. So if I want, so I'll kind of like put here this data structure that is the process control block. That's part of what is needed to build the virtual CPU. So each virtual CPU, each process will have one of these process control blocks going with it. Okay, the process control blocks actually sit inside of the operating system. We can logically think of them as sitting like here. The virtual CPU is really a bit. The process control block's a data structure, but together they make a virtual CPU. Okay, so we've gone over, we should quit there. If you got any questions, I'll put this picture up on the website. Refresh your memory by going back and looking at this picture. Try to think about the logic of what this picture's telling a story. try to reconstruct the story the picture's telling. If you can reconstruct the story this picture's telling, you're understanding modern operating systems. But we have to add more to it. Okay. All right. So I will. Oh, I have to. Let's see. Did I add? Yes. Yeah. There's the reading assignment. So you should start reading this chapter. We're covering right now these two chapters simultaneously. We are actually talking about, from the point of view of the textbook, chapters 4 and 6 simultaneously. Okay, so I'll go ahead and quit there. And if you have any questions, I have office hours tomorrow afternoon, or send me an email. But please look at the picture and think about the picture. Think about the picture while you're reading the book. It might actually help. I think these pictures would have been nice if they were part of the textbook. Okay, and if anyone can draw better pictures than me, yeah, if you can draw your own pictures and you think they're better than mine, I'd like to see them, because I think these are I don't think these are great pictures. The ideas that are in them are all good. I wish I knew how to draw better, more elegant looking pictures. Okay, all right, so I'll stop sharing and we'll meet again on Wednesday. Okay, bye bye.